Sorry. Hi everyone, I'm Chuan Li. I'm going to present our work Learning Weight Uncertainty with Stochastic Gradient MCMC for shape classification. This is a joint work with my level-mates and my PhD advisor, Professor Lawrence Curry. So shapes in the real world manifest rich variability, which prevents the traditional hand-engineered features from generalizing to a broad range of applications and tasks. Recently, deep learning has been applied to learning the representations of shapes. The standard way to train deep neural nets is stochastic gradient descent with backpropagation. While this is popular, it often appears a problem of overfitting. So to reduce overfitting, we consider framework of Bayesian learning, which means we are going to learn the weight distributions of the deep neural nets instead of trying to obtain the single point estimation of the model parameter. One standard way to approximate the posterior distribution is Markov chain Monte Carlo methods. Actually, MCMC methods has been were very popular a decade ago with applications in segmentation and correspondence. But the traditional MCMC methods are not scalable, meaning that it's difficult to directly apply them to tangle today's big data. So one of our primary goals is to bring MCMC back to the CV community, along with high scalability. In particular, we focus on stochastic gradient MCMC methods. So how could we implement SG-MCMC to train deep neural nets? There are two main steps. The first step is in the training stage, we just need to add Gaussian noise to the parameter update of SGD. And in the testing stage, we need to do model average over the predictions using multiple model samples. So if you are interested to study further about SG-MCMC methods, the table will guide you for the recent relationship between them. So another contribution of the paper is to provide the Bayesian interpretation of dropout from the perspective of the MCMC. In particular, we show that dropout and SGLD share the same form of update. The only difference is the level of the injecting noise. We also could combine binary dropout with SG-MCMC, which can be interpreted as learning weight uncertainty of mixtures of deep neural nets. In practice, one can also use spatial normalization to accelerate SG-MCMC. So to validate the proposed methods, we did a lot of applications in 2D and 3D shape classification tasks. This including the recent Shrek contest and the ShapeNets dataset. There are two interesting observations. One is the use of Bayesian methods slows down learning initially, but in the end, the increased uncertainty will prevent overfitting and eventually leads to the high performance. Thank you. That's all.